Okay, well, I gave some homeworks back, and there was a little bit of the material. You have a homework assignment due today. There was a little material that we hadn't gone over yet.
That's all right.
Shall we go over the Hamiltonian circuit stuff before we ask questions about the homeworks?
Yes.
All right. Let's postpone questions for a few minutes then. And let's take a look at our equation sheet here. 19.11.1 is the definition of a complete bipartite graph. Now, do you remember what a bipartite graph was?
Yeah.
What was it?
It's like a graph with like two pots.
Yeah, two parts. That's correct. And in fact, what is divided into two parts? The vertices or the edges?
Vertices.
The vertices are divided into two parts. And what is that division called? The dividing into two parts? It's called a what of the set of vertices?
Bipart.
It's a partition.
All right.
Okay, so it's a partition. Which all right. So there, and what happens is every edge goes from a vertex in one of the sets to a vertex in the other set.
Wait.
Every edge is incident. Remember incident? Every edge is incident on a vertex from one of the sets to a vertex in the other set. So there's no edges from one vertex to another vertex that are in the same set. And we had examples of that. And now what we're defining here in 19.11.1 is the only difference here is the word complete, right? So, and we have this notation K, M, comma, N. So let's do some examples. K, 3, 2. So what is the N and the M? What is this 3, 2? What does this 3 mean? And what does this 2 mean?
Three is M. Vertices.
Number of vertices in what?
In a bipartite graph.
No, there's not 3 vertices.
Wow.
And so, in which one partition has M. Okay, so one partition has 3, and then what's this? The other one has 2. So what happens, what this would look like is there would be 3 vertices in one set and 2 vertices in the other set. Okay, so it would look like this. And there can only be an edge from this one to one of these to one of these, between one of these and one of these, not ever between here and here, for example. And the thing that makes it complete is what? What's the thing that makes it complete? Yeah, but what makes it complete?
Like the top left one has to go to the other two, and
Yeah, there has to be a maximum number of edges, right?
yeah.
So
For a bipartite.
for a complete bipartite.
Yes.
So this would be a picture of the of K32. And K33 would look like this. So there would be an edge between this one and every one of these. Then there would be an edge between this one and every one of those. And then there would be an edge between this one and every one of those. So this is what the K33 graph would look like.
You have like a tripartite?
Oh, there is no such. I mean, it's not as useful. It's not as useful. The reason we categorize these is because these are useful. There are situations in real life where you have connectivity. You want to have connectivity like this. Now, the next concept that we want to describe is what is called a Hamiltonian path and a Hamiltonian circuit. Okay, so and 19.11.2 is defines what a Hamiltonian path is. Part A defines what a Hamiltonian path is, so let's take a look at that. So a Hamiltonian path of a graph or a digraph is a path that contains each vertex exactly once except that the end vertices of the path may be the same. Now, let's think about that. What this says is that if you have a Hamiltonian path, you can't, once you visit a vertex, once the path goes through a vertex, it can't go through that same vertex again. Are you with me? Now, the reason, and then part B is a Hamiltonian circuit. A Hamiltonian circuit is a Hamiltonian path that is a cycle. So what makes it a cycle? What makes a path a cycle?
Vertice end and start the same place.
It's the same, yeah, the path starts and ends on the same vertex. Right? Now, why is this important? Why are Hamiltonian, actually it turns out Hamiltonian circuits are quite important in practice. And in fact, there is a famous problem, 19.11.2. A famous example is called the traveling salesman problem. Traveling salesman problem. All right? So here's the situation. What happens is, suppose that you're working for a company, and you're salesman, and you have to make sales, and so you're working out of your home office in some city, right? And suppose you have like the western region of the United States, okay? And you have to service all of these cities in like California, Oregon, and Washington, and Nevada, say something like that. All right, and say that's your situation. I mean, that's your territory that you're responsible for. So here's what you want to do. And you fly by, let's say once a month you have to visit every, location in a number of cities in the western United States. So you have a map of airline routes, right? And obviously what you want to do is, in order to service each one of your cities that are located in the western United States, you want to catch a plane and fly to one, and then fly to the next one, and 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 then eventually fly back home. Well, it's obviously going to cost you a heck of a lot more. I mean, it wouldn't make sense for you to go from city A to city B, and then back to A, and then to C, and then to D, and then to C, and then, you don't want to have a whole bunch of repeat cities that you visit, because once you've serviced that one city, you want your next flight to be one that you haven't visited before, to save your cost, right? But on the other hand, you do want to visit all of them. So basically what you're looking for is a Hamiltonian circuit. You see, it visits each vertex exactly once. Now, in this situation, it doesn't matter if there are some airline routes between two cities that you don't use. Are you with me? So do you see that this is basically a different problem from an Euler circuit? Okay, so here, actually, let's before I talk about that, let me summarize then what this traveling salesman problem deals with. A vertex in the graph represents a service point, like a city, like a city where you provide the service, and then the edge would be a road or an airline route. Edge would be a road. It could, instead of being a map of an airline, it could be a map of, you could be driving, right? And the roads, and the edge would be a road or airline, or railroad, airline route. Okay? And now the difference between, so let's think about the difference between a Hamiltonian circuit and an Euler circuit. What did we have for an Euler circuit? Yes, what we did is each edge was traveled exactly once. Each edge was traversed exactly once. On the other hand, a Hamiltonian circuit, what's the difference between an Euler and a Hamiltonian? Yeah. So the difference is, this is each edge traversed once. On the Hamiltonian is each vertex. Each vertex is visited exactly once. So that's the big difference between them. All right. Now let me give you an example of a Hamiltonian circuit. I'm going to draw kind of a complicated example, but it's a common one that's used in all the books, and it's a nice one. I can see why it's common. What we're going to do is we're going to have a what is it called? The baseball home plate? Pentagon. So we're going to start with the pentagon here, and we're going to have an edge go off straight out from the center from each one. And then from that, and then from each one of these, we're going to have an edge here like this. Like this. Are you with me? And then this one, and now every other one, every middle one of these goes out like this. Yeah. And then we put a hole, and then we put one along the whole outside of the whole thing. There. My shape is a little distorted here, but it doesn't matter. Distortion doesn't matter on these graphs, right?
Looks a lot better than mine.
So here's my question. Does this have a Hamiltonian circuit? Actually, let me ask you another question. Before I ask you. Does it have an Euler circuit?
Yes.
You think? Come on. Oh, I'm so disappointed.
I'm trying to count. One, two, no.
Does it have an Euler circuit?
No.
How do you know it doesn't have an Euler circuit?
It's got vertices of odd degree.
Because it's got many vertices of odd degree. There's odd degrees all over the place.
So they all have to have even degree.
They all have to have even degree for it. So you know right away it doesn't have an Euler circuit, right? The question is, because there's odd degree. Here's degree is 3, degree is 3. In fact, as a matter of fact, every single one is degree 3.
All of them have to be even degree.
All of them have to be even degree to have an Euler circuit. And we also know that the number of vertices of odd degree is even. So anyway, but let's back to our original question. Does this have a Hamiltonian circuit? Okay, you think so. All right. Can you... Here, let's... Okay, so show me. Where do you want to start? This is a nice puzzle. Do you think anyone else think it does? Or have you found one yet?
I don't know, there is probably. It'd be a useless example if it wasn't.
Well, come on. Give me your best shot.
I think I found it.
Okay. Where do you want to
Start at the top right.
We'll start at the top right. Okay.
I was going to say bottom right.
Now go down from the outside.
Here? Outside?
Yeah. Then go in a layer and up.
Like there?
Yep.
Okay.
And keep going up. Now go left. Now go down around the inner pentagon.
Here?
Yep. And now right. And left. And now down. And then left. And then out. And then up. And then back in. Then down. Right. Up. Left. Up, right. Straight up. And back. Finish.
Yeah. I think that's it.
Yeah. You can almost do anything.
Yeah, well, there's many. There are many different ones. There are many different ones. Okay? Now, how did you determine whether or not there was a Hamiltonian circuit?
It's a fake guess. I guess.
Well, no. Well, actually, what you did is you discovered one.
Well,
You by trial and error, you discovered one, right?
Yeah, you just kind of reason.
Okay, but
It's so good, we didn't have one up there.
but here's a fact. I'm not going to prove this, but here's a fact. How do we know that this doesn't have an Euler circuit? That's very easy.
Odd degree thing.
Yeah, the odd degree thing. We just look at to see if there's any vertices that have odd degree. We know it doesn't have an Euler circuit. Now here's a fact. There is no simple test. Isn't this an amazing? No, this is quite an amazing problem. There is no simple test like there is for the Euler circuit to where we can just say, oh, well, the degrees of this or the number of edges, or maybe the ratio if there's this many edges to this many vertices. I mean, you can come up with all sorts of theoretical things, to wonder about. But the fact is, there is no simple way to know if an arbitrary graph has a Hamiltonian circuit.
How would you program it then?
That is a really good question. How would you program it to find the Hamiltonian circuit? Because if there's no even a simple way to know, then how can you have the computer find it? Okay, so first fact, no simple way to know. No simple way to know. There is no simple way to know if an arbitrary graph has a Hamiltonian circuit. If an arbitrary graph,
What about a finite graph?
even if it's finite, has a Hamiltonian circuit. And the thing that's the thing that's bad about this is that it's such a practical problem. I mean, in practice, okay, and furthermore, check this out. You asked about what about the computer? There are algorithms to compute the Hamiltonian circuits. But what you have to do is basically trial and error. It has to.
Yeah, you're doing insane trial.
Yeah. So all algorithms to compute Hamiltonian circuits. So check this out. All algorithms to compute. By compute, I mean discover, like what you did. You computed the Hamiltonian circuit. All algorithms to compute the Hamiltonian circuit are, get this, are big omega 2 to the n. Now, what is big omega? Bounded above or bounded below?
Oh, below. No.
Oh, yeah.
O is over, omega is bounded below. And what does that mean? If it's bounded below, that means that it can't be better. It can't be faster. This is the best you can do is 2 to the n. That is exponential, where n is the number of vertices. Okay, our big omega to the n, i.e., exponential. So those are very, very difficult. They are very, very difficult. So bounded below means none are better. This is parentheses. This is bounded below. Bounded below. None are better. And it's especially compounded by the fact that there might not be a Hamiltonian circuit. And furthermore, what you want to do from a practical perspective, what you want to do is, you want to find the one that has the minimum cost. So there might be another Hamiltonian circuit that goes through fewer edges, or the salesman would not want to go from Los Angeles up to Seattle, and then down to San Diego, and then up to Portland, and then you see what I mean? Because you would be,
How's the graph?
because
Because the graph doesn't quite the distance.
that's a good question. So what has to happen, the way that works is we have to have additional information, and that, to solve that problem, each edge has to have a cost. And so it's called a weighted graph. And so this could cost like, this would cost like, well, you put the label on.
I mean the phone, how we had the ordered tuple.
Yeah, then each edge would have three things: this vertex and the cost. Okay, so it would be an ordered triple. Each edge would be an ordered triple. And see, this might be like maybe like $100 for the airline ticket from here to here. This could maybe be $50 for the airline ticket from here to here. This could be like maybe $75 for the price of the ticket from here to here. Or maybe these could be, if it was roads, maybe this could be 100 miles between this one and this one. This could be 50 miles between this. And you want to minimize the number of miles you drive. Or on an airline, you want to minimize the number of costs. And there are algorithms to do that, to find the minimum cost, of a Hamiltonian. But for a Hamiltonian circuit, it's this. And that's an even more difficult problem to solve when you add the weights to it and you try to minimize the cost. All right? So, with that in mind, what about the questions about the homework?
I just have questions on 19.4 now.
On the proof?
Yeah.
Oh, okay, so let's bring that up. What was it that we were trying to prove?
I get really
Which one is that?
19.4.
Oh, 19.4, here it is. In a digraph or multigraph, the number of vertices of odd degree is even. Okay, so the hint that I gave you was to do
Mathematical induction.
mathematical induction
On the
on the number of
edges.
edges.
Base case.
So the base case, so you assume that you have a bunch of vertices, doesn't matter how many.
Do you have to write that?
Yeah.
You have to say.
You're going to do, we're going to do mathematical induction on the number of edges. So in the base case, we assume no edges, right? So if there are no edges, oh, and what must we prove for the base case? That the what? That the number of vertices of odd degree is even. So why is that true in the base case?
All vertices have degree of 0.
All? Yeah, that's right. Because if there's no edges, all vertices have degree 0. So how many have odd degree?
None have both.
So 0 of them have odd degree. And furthermore, what do you know about 0? 0 is what kind of a number?
It's even.
Yeah, 0 is even. So therefore you prove the base case. Now the tricky part is how to set up the inductive part, because you have to write, it involves a lot of writing.
Oh, yeah.
So what is it that we're trying to prove, and then what is it that we're assuming
We have to prove the number of vertices
Vertices.
of odd degrees
is even in a graph with how many edges?
n plus 1 edges.
We have to prove that it's true, yeah, on a graph with n plus 1 edges, assuming what?
Assuming that it's true.
That the number of
Yeah.
no, please don't say base case on this. Assuming that the number of vertices of odd degree is even in a graph with what?
With no edges.
0.
No,
N edges.
with n edges.
Okay.
Why do students always get mixed up the base case with the inductive case?
Because that's.
Because I haven't seen n anywhere else in the problem.
We always start with n and prove it with n plus 1.
Okay, so we assume.
In the inductive step, is that not right?
Yeah, we
Don't we
do.
prove n plus 1 using
I
n?
just label it.
Exactly. We prove n plus 1 using n. So we have to prove that a graph with n plus 1 edges, that the number of vertices of odd degree is even, assuming that the number of vertices of odd degree is even in a graph with just n edges. Are you with me? And you just have to write that out in English.
That's a lot of writing.
That's all right. You can do it. You can do it.
Prove that.
How do you prove that?
Like that.
Oh,
No.
It's a-
Actually, so imagine here. Imagine imagine all these vertices, right? With n edges. Okay? And what do you know about that with n edges? You got n edges, and what do you know about that graph that has n edges? What do you know about it?
The number of odd degrees
Is even. So just imagine, some of those are odd, some of those are even, some of those have odd degree, some of the vertices have even degree, right? There's a bunch with odd, there might be some 7s, some 5s, some 2s, some 3s, some 4s. Some of them have odd degree, but by assumption, that the number of vertices with odd degree is even in that one. And now what are you going to do? You're going to add an edge, exactly, because you're going to add one edge to that one, and you're going to get it to a graph that has n plus 1 edges. Are you with me? Now think about it. You've got all those vertices there. Some of them have odd degree, some of them have even degree, right? But you know that the number of vertices of odd degree is even. There's an even number of those ones that have odd degree.
There's 3 cases. Yeah.
There are 3 cases. Very good. Okay, so now I think you've got it, right? There are 3 cases because there's 3 ways in which you can do what?
But you can add.
In which you can add an edge. And what are the 3 ways in which you can add an edge?
Odd to odd, even to even.
You can connect an odd to odd, or you can connect an even to even, or you can connect an odd to even. So what you have to do is in each one of those cases, you have to describe what happens to the degree,
The number of
vertices with
with odd and even degree. Yeah. How does that change it? And then if you can argue how that changes it, if it keeps in each one of those, you should be able to argue logically that the number of vertices of odd degrees, it will still be even, no matter which one of those 3 cases you use to connect. Now, isn't that neat?
if that's the word you want to use, yeah, sure.
I think that's just,
Splendid.
So can you start it by saying you have a graph with n plus 1 edges that connects an odd to.
no, you start with a graph that has n edges.
So we start it and then we add another one.
Yeah, because that's what we said in the sentence. Remember, that's what we said. We said that we have to prove.
But don't we always do it the other way? With
No,
fraction?
no. We prove for n plus 1, assuming it's true for n. No, add one edge. Add one edge.
There's 3 cases. Yeah. You gotta say you add 1 edge before you start the case stuff.
You have to understand if you understand the logic, the English shouldn't be that hard to write.
It's not. It's just, normally there's a structure to it.
But now you got the structure, right?
I think I kind of followed it.
But you're right, there are 3 cases.
Yeah.
And you have to analyze each one of those cases and ask yourself, well, how does the number of, does this one increase the number of vertices with even or odd, or, how does it change it? Okay, exercise 19.4.
Yeah, I don't like guessing.
There's no easy way to find out if it has a Hamilton sign.
There is though.
So you have to
Right,
draw a graph and figure it
right.
out.
Yeah, some of those.
Four is not to do with Hamilton.
Yeah, what I suggest you do is try to find one,
But-
and if you can convince yourself that it's
I'm
impossible.
convinced that it works.
Does it have an odd number of edges?
No.
Then it has to in the problem.
Wait, it does?
Yeah.
I thought it said even
That's
number
why
of
it's
edges.
so difficult.
No. Odd number edges, yes. Even number vertices.
Really?
Yeah.
And it's connected.
What?
And it's connected.
And it's connected and has an Euler circuit.
I don't believe it.
No.
You should not tell them. We have somebody who has discovered a secret, claims to have discovered. For this existence proof, is all you need to do is come up with one, right?
Yeah.
But if you think that if you think that he might not be right.
As long as I might be breaking the rules.
Can I check your work?
This is a good question. Actually, a lot of people get this one wrong.
Is it because one actually doesn't exist?
I'm not saying. Maybe you're breaking the rules. Yeah, that's just a trial and error. There's nothing for me to give you a hint on that one other than just trial and try it, trial and error.
An Euler circuit can reduce vertices and not edges, right? Yeah.
Right. And then for 1919, there's 4 parts to the problem, and you just have to. I mean, with that one, with 1919, I mean, he's not asking you if it's possible. He's asking you to do something, right?
It is possible.
For 1919.
It's
Yeah.
always possible.
Oh, it says, give an example.
Yeah. So he's not going to ask you to give an example for something that's impossible.
Yeah, that would just not make sense.
Well, depending on how devious you are. Because I do want to show you one more thing. I want to introduce you guys to something. This is, unfortunately, we don't have time to actually give you an assignment on it. But I just want to show you something.
You got no final.
Always the question, is it going to be on the final?
But depends how much it takes.
This is, we've got 10 minutes, and I want to introduce this to you, just because it's a really famous problem. that deals with graphs. All right? This is called Dijkstra's shortest path algorithm. What I'm going to do is I'm going to put a graph here. I'm going to label this 0, 1, 2, 3, 4. I'm going to go from here to here is 10. Here to here is 2. This is 3. This is 1. This is 4. This is 6. From here to here is 9. From here to here is 2. And from here to here is 7. Now, let me ask you a question. So here is a graph, and instead of wanting to do a Hamiltonian circuit, we're not going to tackle that problem. What we want to do is, this is called the shortest path problem. And what these numbers represent are, let's say that these are roads and these represent miles in between points on a graph somehow. Okay, because some of the, there's mountains, and so some of the roads have to go around mountains and, whatever. All right? Wnow, let me ask you this. What is the shortest route? What is the shortest way to get from, what's the shortest way to get from 0 to 1? What's the shortest way to get from 0 to 1? So, in other words, here's what we want to ask. What is min, we're going to call this min 0, 1. What's the shortest way? What's min 0, 1? Really?
Yeah, directly.
It's the only way.
No, you're right. It's the only way. Wait.
Did you direct them the right
Wait,
way?
did I do it?
You put the arrows on one, maybe.
Oh, I left one out.
Oh.
Ah.
Yeah, sorry.
That's a-
I left one out. Yeah, I left one out.
Okay, so
Now what's the min?
3, 3, 1.
Yeah, 0 to 3, 3, 1. So the cost of that is 5 plus 3 equals 8. Now, in order to determine that, we couldn't just look at this one to go from here to here. The number, we couldn't look at the number of hops between here and here. It's actually cheaper to go 2 hops because 5 plus 3 is 8, and that's less than 10. How about the min between 2 and 3? How about min 2, 3? Between 2 and 3. In other words, what's the shortest way? What's the shortest way to get from 2 to 3?
2 to 4, to 4 to 0, to 0 to 3.
So what is that? What plus what plus what?
4 plus 7 is 5.
Yes. That's 4 plus 7 plus 5. And if you add that all up, that's 16, right?
Yeah.
So it would, to go from 2 to 3, you go from here to here.
It's the only way to go.
No, you could go here, here, and here.
Yeah, but
Or here, anyway.
any logical person.
Well, yeah, but you have to take into account the weights, right? Okay, so now here's what's interesting. Dijkstra, Dijkstra, very famous computer scientist. He now the question is, did he invent this algorithm or did he discover it? What do you think? Do you think algorithms are discovered or do you think they're invented? Are they there waiting for us to find them, or do we actually or are they an invention of our own minds?
If it's utilizing already existing
Exactly, which it is. So it's
concepts,
discovering.
that's it.
You say algorithms are discovered. Oh wow.
What do you say? You said
I don't know. I never have been able to figure it out, but
Because they're already there if we already know all the operators or whatever that we're going to be using. But you just have to figure out the way.
but we invented the operators, right?
Right.
Is
Well,
mathematics invented or
Yes.
discovered?
debatable.
Because it's a mathematical. You see what I'm saying? In other words, are theorems invented or discovered? Did we construct, is mathematics just a construct of the human mind, or does it actually have some basis in reality?
Well, it definitely has a basis in reality.
Well, you think?
It has an application.
Yeah.
Well, it has application just as the model. Well, we're getting, well, okay, we're a little off topic here. So here, we denote by min BC the minimum cost over all BC paths. So min BC equals, check it out, it's the min over p such that p is a BC path of the cost dot p. Right? And by cost, what we mean is we add the weights. These are called weights. We add the weights along the path to get there. Now, this is a very interesting algorithm. I want to see if I can give you a flavor of this algorithm. It's a famous one. Okay, we're going to do a little time warp here. We're jumping back to the future, fall of 2022, and I have prepared a sequence of slides to do a little trace here of Dijkstra's shortest path algorithm. So here on the lower left corner of the slide, I've reproduced the graph. It's a digraph that we will trace. We will do a trace of min 0, 1. So we're tracing min BC where the value of B is 0 and the value of C is 1. So the values that we're going to trace are, there's an array L, L sub 0, L sub 1, L sub 2, L sub 3, and L sub 4. And then F is a set. U and V are integers that represent vertices. So we'll start off at the beginning here. Next slide shows the first statement is for all vertices V do L sub V gets infinity. So that sets the each value in the L array to infinity. All right, and then the second statement says L sub B comma F gets 0 comma V. So the value of B is 0. So this statement sets L sub B to 0. So you see L sub 0 gets 0. It used to be infinity, now it's 0. And the set F gets the set of all the vertices. So you see the set F is the set of vertices 0, 1, 2, 3, and 4. All right, then we next statement we do the guard for the do loop. So the question is C an element of F? That's the guard for the loop. And the value of C is 1, and sure enough 1 is an element of F. And therefore we do the loop. All right, so now the next statement says let U be the vertex of F with minimum L value. So first of all, let's take a look at all the vertices in F. It's 0, 1, 2, 3, and 4. So that means that the values that we have to look at in the L matrix is L sub 0, L sub 1, L sub 2, L sub 3, and L sub 4. And those values are 0, infinity, 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 and infinity. And the smallest one of those is 0. 0 is less than infinity, all those other infinities. And it's L sub 0 is the one that is the minimum, is 0, and that therefore U gets 0. So that's what happens, that's how we say, that's what happens when we do let U be the vertex of F with minimum L value. All right, so now the next statement is a set difference. So we take the set F, and what it gets is the set F minus the set with the element U in it. So as we see on this next slide, F is now no longer has the 0 vertex in it. Now the next slide says, the next statement rather, says for each V adjacent to U. Now this is the way this statement works. If the current value of U is 0, right? So the question is, which vertices are adjacent to 0? Well, we can see on this figure that there is an edge from 0 to 1 and an edge from 0 to 3. Therefore, 1 is adjacent to 0 and 3 is adjacent to 0. So this loop is going to execute twice. Once for v being 1 and once for v being 3. So on this next slide, we see that we set v to 1 because there is an edge from 0 to 1, because 1 is adjacent to vertex 0. Vertex 1 is adjacent to vertex 0. So now what happens in the body of this loop? It's one statement. And it says L sub v gets L sub v min L sub u plus w u comma v. So what happens? What happens when this statement executes? Well, what we do is we take a look at the current value of L sub v, and because v is 1, L sub 1 is infinity. So L sub 1 is going to change. What's it going to change to? Well, it's going to change to be the minimum of the current value of L sub v, which is infinity, and L sub u plus w u comma v. Well, w u comma v is the weight of the edge between u and v. U is 0, v is 1. So the edge, that edge has weight 10, or cost 10. And so there, consequently, L sub 1 gets the minimum of infinity and 10 plus 0. 10 is the minimum of between 10 and infinity, so L sub 1 gets 10. Then we do the loop again. So we come back here, and what's the other vertex v that is adjacent to 0? Well, it's vertex number 3. So consequently, v is 3 because there's an edge between 0, because 3 is adjacent to 0. That's the second one that is adjacent to u. All right. So now what happens in the body of this loop this time? Well, what's going to change? L sub v is going to change. What's the value of v? That's 3. So L sub 3 is going to change. What's the current value of L sub 3? It's infinity. So what is the minimum of infinity and 0 plus 5? The answer is it's 5, and consequently L sub 3 gets 5. Are you with me? Okay, and now what happens is we are done with that for loop, and so we exit, so we get to the bottom of the do loop, and we go back up to the top with the test, the guard. Now, is C still an element of F? Well, C is 1. 1 is still in F, so we got to keep on trucking. Now, on the next slide, we see what happens. We execute the statement. Let U be the vertex of F with minimum L value. Now, what are the vertices of F? They are 1, 2, 3, and 4. So we have to compare the values 10, infinity, 5, and infinity, because those are the values of L1, L2, L3, and L4. Now, obviously, if you got 4 numbers, 10, infinity, 5, and infinity, the smallest one is 5. Now, which one is 5? It's L sub 3 is 5. Therefore, U is 3. Are you with me, sports fans? Now, what's going to happen when the next statement executes? That statement is F gets F minus the set U. What's the value of U? The value of U is 3. So the set difference is going to be F without the element 3 in it. So here, that is shown in the next slide. So F no longer has 3 in it. And then the next statement says, for each V adjacent to U, do, and so now the question is, what is U? The value of U is 3. So which vertices are adjacent to 3? Well, if you take a look at vertex 3, we see that there is an edge from 3 to 1, an edge from 3 to 2, and an edge from 3 to 4. Consequently, the vertices that are adjacent to 3 are 1, 2, and 4. So this for loop is going to execute 3 times. once with a value of v being 1, once with it being 2, and once with it being 4. So here's the first one is, you see there's an edge between 3 and 1. So that means that our v, the first time through the for loop, is going to be 1. And now what is going to change? The body in the for statement that executes is L sub v gets something. What is the value of v? That's 1. So that means L sub 1 is going to get something. Well, what is the current value of L sub 1? The current value of L sub 1 is 10. So it's going, what is it going to get? It's going to get the minimum of 10 and what quantity? Well, it says L sub u plus w sub u comma v. Well, what is w sub u comma v? Well, u is 3, v is 1. W sub 3 comma 1 is the cost of the edge from vertex 3 to vertex 1. So that's 3, you see. So L sub 1 is going to get the minimum of L sub 1 and the quantity L sub 3 plus the cost of the edge between 3 and 1. Well, the cost of the edge between 3 and 1 is 3. So 5 plus 3 is 8. So it's the minimum of 10 and 8. And consequently, L sub 1 is going to get 8. So it will no longer be 10, but instead it will be 8 as shown in this slide. Are you with me, sports fans? And so now which other vertex v is adjacent to vertex 3? As shown here, there is an edge from vertex 3 to vertex 2. So consequently, the next time through the loop, v is 2. So now, what is going to change this time? L sub 2 is going to change because v has a value 2. And what is it going to change to? It's going to change to the value, the current value, the minimum of the current value of L sub 2, which is infinity. Well, obviously, it's going to change to something less than infinity. And L sub u, which is, because u is 3, L sub 3 is 5. So what is 5 plus the cost from what is the cost from vertex 3 to vertex 2? It's 9. So 5 plus 9 is 14. So consequently, L2 gets 14 because 14 is obviously less than infinity. Now, what is the next vertex that is adjacent to 3? Well, as shown on this slide, there is an edge from vertex 3 to vertex 4. And the cost of that edge is 2. So what's going to change this time? Well, the value of v is 4, so L sub 4 is going to change. Well, what's the current value of L sub 4? It's infinity, a very big number. So the minimum of infinity and L sub u plus w of u comma v. Well, what is L sub u? Well, u is 3. The current value of L sub 3 is 5. 5 plus 2 is 7. 7 is less than infinity. And consequently, as shown in this slide, L sub 4 gets 7 as a result of that assignment statement. Now we have analyzed all of the vertices v that are adjacent to vertex 3. So we end this for loop and we go back up to the top of the outer do loop with regard c as an element of f. Well, here again, c has a value 1. 1 is still an f, so we've got to keep on trucking. So now what do we have to look at? See, can you anticipate what we have to inspect? The next statement says that u be the vertex of f with minimum L value. Well, how many vertices do we have in f? What are they? They are 1, 2, and 4. So what values do we have to look at? As shown in this next slide. We have to look at L sub 1, L sub 2, and L sub 4. So the values that we have to look at are 8, 14, and 7. And the smallest of those is 7. And L sub 4 is the one that has the value 7. And consequently, u gets 4 because u is the vertex of f with the minimum L value. Are you with me? Now what's going to happen on the next slide? We're going to take out that vertex 4 from that set F. So there, F no longer has 4 in it. Now it only has 1 and 2 in it. Our value of U is 2. We are analyzing the edges that are adjacent to vertex 4. So on this next statement, for each V adjacent to vertex 4, well, what's adjacent to vertex 4? Can you see the pattern now? Well, 4 has an edge. There is an edge from vertex 4 to vertex 0, and there's another edge from vertex 4 to vertex 2. So those values that are adjacent to vertex 4 are vertices 0 and 2. So here shows the one between 4 and 0. It has a cost of 7. Now what is going to be computed in the statement, in the for statement? L sub v is going to get something. What is L sub v? What is v? V is 0. What is L sub 0 going to get? It's going to get the minimum of the current value of L sub v, which is 0, and what? The current value of L sub 4, which is 7, plus the cost of the edge from 4 to 0, which is another 7, which is 14. Well, if the current value is 0, 0 is less than 14, so consequently, as shown in this slide, the value of L does not change because the minimum of 0 and 14 is just 0. Now, what about the other edge that is adjacent to vertex 4? That would be vertex 2, as shown in this slide. And what is the cost of the edge from 4 to 2? That's 6. And so what is going to change? The value of L sub v, because v is 2, what's going to change is L sub 2. Now let's pause a moment here and see what's going on. The current value of L sub 2 is 14. Now where did that 14 come from? That 14 came from 5 plus 9. In other words, the cost of the path from vertex 0 to vertex 3, which is 5, plus from vertex 3 to vertex 2, which is 9, and that 5 plus 9 is what gave us the 14. Basically what happened at that point in time is, at that point, the shortest path that we have discovered from 0 to 2 was from 0 to 3 to 2, with the cost of 5 plus 9, which is 14. Now what we are doing is we are discovering a shorter path. We are inspecting the edge from vertex 4 to vertex 2, which has a cost of 6. And we already know that the shortest path that we have detected between 0 and 4 is from 0 to 3 to 4, which is 7. Now, if we go from 0 to 3 to 4 to 2, then that cost will be 5 plus 2 plus 6, which is 13. Whereas before, when we went from 0 to 3 to 2 directly, that was 5 plus 9, which is 14. But 13 is less than 14. So what's happening here, as shown in this slide, is that the minimum, we have a new minimum. You see, the new minimum of L2 is 13 because we have discovered a shorter path between vertex 0 and vertex 2. Even though it takes more hops to go from 0 to 3 to 4 to 2, it takes more hops. Still, the fact that when you go from 0 to 3 to 2 directly, that 9 is more expensive than the 6 plus 2, which is 8. So consequently, you see, the newly discovered minimum cost to vertex L2 is 13. And so now we have terminated our for loop, and we go back to the top of the loop, the outer do loop again. C is 1. 1 is still an F. We have to keep on trucking. So we let U be the vertex V with minimum L value. So what values do we look at? We look at the 8 and the 13. 8 is less than 13. L sub 1 is the 8, and therefore U is 1. So now we are going to go to vertex 1 and investigate all of the nodes that are adjacent to vertex 1. So first we have to do F gets F minus the set U. The value of U is 1, so we have to get rid of the 1 from vertex 1 from set F, as shown here. And now the next line is what for each vertex, for each V adjacent to U. So what are the vertices that are adjacent to vertex 1? Well, there's an edge from 1 to 2, and there's an edge from 1 to 3. So, as shown in this slide, we will first consider the vertex 2, which is adjacent to 1, with an edge that has a cost of 1. So now, in the body of the for statement, what value is going to change? Well, the value of V is 2. That means that L sub 2 is going to change. Now, wait a minute. L sub 2 has changed several times before. The current value of L sub 2 is 13. Where did that 13 come from? Remember that 13 came from the path from vertex 0 to vertex 3 to vertex 4 to vertex 2, which was 5 plus 2, which is 7, plus another 6, which is 13. What's going to happen now is that we are discovering yet another shorter path, a shorter cost path to get there. Because the current value of V is 2, so what is L sub 2 going to get? It's going to get the current value of L sub 2, the minimum of that value, and L sub U, which is L sub 1. Now what's L sub 1? That's 8. Now where did that 8 come from? That 8 came from going from vertex 0 to vertex 3 to vertex 1. 5 plus 3 is 8. That was the cost of the shortest path that we have found so far. That 8 plus 1 is 9. So now L2, as shown in this slide, is going to get the new value of 9. Now, what other vertex is adjacent to vertex 1? Well, as shown in this slide, it's vertex 3. And what is the cost of the edge from vertex 1 to vertex 3? It's 2. And so now what's going to change in the body of the for statement? L sub V, which means L sub 3 is going to change. What's the current value of 3? Of L sub 3? It is 5. So what is L sub 5? What is L sub 3 going to get? It's going to get the current value, the minimum of the current value, which is 5, and L sub U, which is 8, plus the weight, which is 2, which is 10. But 5 is already less than 10, so the value of L does not change as shown in this slide. So now we have terminated the for loop. We go back to the outer loop as shown here. C is 1. Oh, wait a minute. C is no longer in F. So therefore the complete algorithm terminates. We terminate the outer loop. And the result is the value of L sub 1 is 8, because what we were computing was min 0, 1, which was the cost of the minimum path from vertex 0 to vertex 1. Now you may have noticed that in the process of doing this, we actually even found the cost of the minimum path between vertex 0 and vertex 2. And in fact, our author points out that if you change the guard in the outer do statement from C is an element of F to F is not equal to the empty set, that the values that you get, the final values that you get in all of the values in the L array are the minimum costs of the paths from L sub 0 to every other one in the array. I also encourage you to look at the material in our textbook. Our author provides a proof that Dijkstra's minimum cost algorithm is correct by describing the invariant, showing that the invariant is true at the initialization of the loop, and consequently that the program is correct at the termination of the loop. Now that we have seen how the algorithm works with this specific example, I think it will be easier to understand the proof of correctness that is given by the author of our book. Okay, so that about wraps it up. And we'll start reviewing, we'll just quit a few minutes early here and see you next time.